Okay, so good morning students. So next topic is tension and compression members, so which is very important for 14 marks, so tension members. So tension member is nothing but a member which carries a tension load. A member which carries a tension is known as tension member, but that load or that member should carry through axis point only, is known as tension member or type. So this is called tension members. Applications. So applications is nothing but where the tension members apply in cable type structures, bracings in buildings, next trusses, next suspended bridges. Okay, so the tension members are applied in cable structures, bracing buildings, suspended bridges and trusses. So in these steel structures or in these structural elements, the tension members were applied in different types of sections. So different types of sections are, first one, angle section, box section, tabular section, I section, channel section, angle section, box section, tabular section, I section, channel section and T section. This is the basic introduction class for tension members. Tension member is nothing but a member which carries a tension through the axis point, is known as tension members or type. Applications is nothing but the tension members were applied at cable structures, bracings in building structures, trusses and suspended bridges. So in these applications it will be in the types of section which is in types of angle, box section, tabular section, I section, channel section and T section. So in these methods tension members were depend upon design strength. So to calculate design strength for tension members, so first we will take only tension members. To calculate design strength of compression tension member, it will be depend upon some strength or some parameters. So we will calculate the parameters for calculating the design strength, but in this calculating the design process for tension members, there will be some modes of failures. Okay, so that modes of failures are first one, gross section yielding. Second one, net section rupture. Third one, block shear failure. So these three are basic modes of failures in tension members. Basic modes of failures in tension members. So in these three will be in page number 32 and 33 in code book. The formulas to determine the modes of failures for tension members were in page number 32 and 33 in code book of IS-800. So first we will discuss about gross section yielding. So first we will discuss about gross section yielding. Gross section yielding. So what is meant by gross section yielding? Steel members without bolts. Steel members without the bolts can sustain about ultimate load. Okay. So the ultimate load for steel members gamma and so gross section yielding is nothing but the tension members without bolts. The tension members without bolts can sustain some ultimate strength. So to find the ultimate strength in gross section yielding, we have Ddss is equal to Fi Ac by gamma m0. So this design strength for Ddss is equal to Fi Ac gamma m0. We know the values of Fi Ac and gamma m0. So please remember this gross section yielding formula will be in page number 32. Okay. So Fi is nothing but yield strength, gross area, and gamma m0 is welding. Okay. So this is the gross section yielding. So now second one, net section rupture. Net section rupture. So the net section rupture is nothing but when the tension members are connected to the bolts. When the tension members are connected to the bolts or by other members. When the tension members are connected to the bolts or by other members, this mode of failure will be developed. So in this, the formula to calculate net section rupture. So in this, to calculate the design strength, the formula will be Tdn is equal to 0.9 FuAn by gamma m1. Tdn is equal to 0.9 FuAn by gamma m1. So this will be page number 32 bracket 6.3. So that will be in 6.2 what is gross section yielding, and this one is net section rupture, which will be in page number 32 6.3. So here mainly we should consider we have these types of bolts which okay. So this is the center to center G. So this is G, center to center, and this is die of the hole or bolt. So this is the center to center distance for G. So here G is nothing but gauge length. G is nothing but gauge length. So to find overall AN, we have the formula for AN is nothing but net effective area. AN is nothing but net effective area. AN is equal to B minus N into Dn plus summation of P square SI by 4GI into T. Okay, so here it is nothing but B minus N value will be number of bolts 1, 2, 2.5, 5, 5.5. So here 1, 2, 3, 4, 5. So 5 bolts. So number of bolts. N is nothing but number of bolts. And the Dn is nothing but dia of bolts. And summation of P SI square is this one. So how many? 1, 2, 3, 4 like this. How many numbers are there? By 4 into T is nothing but thickness. T is nothing but thickness. So you don't need to remember this formula. Why? Because it will be in code book page number 32. While solving the problem, we can neatly, you can get it. Okay. If this is for plates, this formula is for plates. If rods, if it is in rods, that is TDN is equal to 0.9 FU AN by gamma M1. Same 0.9 FU AN by gamma M1. So here AN is nothing but net rooted effective area for net rooted section like rods. This is in plates. This is in rods. Next. If single angle is given, okay, then same TDN is equal to 0.9 FU ANC by gamma M1 plus beta AG0 F5 by gamma M0 will be page number 33 6.3.3. Same. Plates given before formula, rods given this formula, single angle is given, single angle is given, this is the formula. So please remember all these formulas. So FU will be there, ANC, AG0, F5. While solving the problem, we can know the math. Okay.